Okay, good evening. So now this is our 27th lecture, and in the previous lecture we have already started our discussion on the measurement of void fraction, and we will continue the same today as well. So if you recall from the previous lecture, first I have discussed the uh, different forms of void fraction along with their mathematical formulation, and then specifically we have discussed that how X-rays and gamma rays can be employed for measurement of the linear void fraction and the cross-sectional averaged void fraction. Okay, so that is something which we have seen. So now there are certain other methods other than the X-rays and gamma rays which can be employed for measurement of void fraction that we will try to see, and then quickly we will switch our discussion to the flow visualization. Okay. So let's discuss in case of X-rays and gamma rays, our measurement approach was that once the ray is starting from the source, then before reaching the detector there is actually attenuation in the intensity of the ray. Okay, and that attenuation we were actually able to correlate to the formulation of void fraction. Now we will talk about second type of approach, which comes under the category of optical approach, and in this particular method, the device which used for measurement of the void fraction, that is called as optical probe. Okay, so as you know that in case of optical probe also, we will be actually sending some electromagnetic waves on the interface, but whenever these waves are coming on the interface, then at the interface actually we will be having different phenomenon, and the common phenomenon are nothing but reflection and refraction, and typically these phenomena occur simultaneously. Okay, so a schematic representation is shown over here. So here you can see, you can consider this to be your interface. Okay, so if this is our interface, in one side of the interface, say below this line I have presence of fluid 1, and above this say I have presence of fluid 2. Okay, so typically what will be happening, each material has its corresponding value of the refractive index. So the refractive index of fluid 1 is N1, and refractive index of fluid 2 is N2. Okay, once, now if I consider that this is my incident ray. Okay, so this is nothing but incident ray. So this incident ray, if it is actually coming to this interface at an angle of theta I, okay, then I will be having part of the ray which will be reflecting at an angle of theta r, and part of the ray which will be refracting at an angle of say theta t. Okay, now here ki, kr and kt are the corresponding vector directions which represents the direction of incident, direction of reflected, and direction of the transmitted. Okay, typically from our fundamental Snell's law we know that theta I will be equal to theta r, and n1 sine theta I will be equal to n2 sine theta t. So these are the two important relations which fundamentally we know from our optical fundamentals. Okay, now whenever this incident ray is coming, then part of this is reflecting and part is refracting. So of course there will be actually changes in its intensity. So say the changes in its intensity is denoted by R. So R is nothing but intensity of the reflected divided by intensity of the incident wave. Now this R can be divided into two components. One component can be parallel to the direction of incident ray, that is RP, and other can be perpendicular to the direction of incident ray, say that is my RN. Okay, so RP is the this intensity ratio for parallel to the incident wave, and Rn is normal to the direction of the incident wave. Okay, so if we do some geometric manipulations, particularly the trigonometric manipulations, then we will be getting the value of Rp and Rn something like this. So basically these values are nothing but functions of the refractive index, incident angles and theta t. Now one important point is theta t can be replaced from this particular equation in terms of theta I only, and my whole equation, in the entire equation, Rp and Rn will become sole functions of n1, n2 and theta I. Okay, so that is something which is the fundamental idea. Now if we see, so what happens if I see the variation of R as function of incident angle theta I, then we can see the values of Rp and Rn below some critical limit are actually different. Okay, and these are close to 20%. So here you can see Rp is 20 and at theta equal to 0, and Rn is also 20. So it means that the output waves intensity will be nothing but 20% to that of the incident wave. Okay, so here these Rp and Rn, after an angle of theta incident greater than theta c, they almost reach to their unity value. It means that whatever the amplitude of the initial incident wave is there, same will be their amplitude of the final reflected wave. Okay, so typically this plot is given for n1 equal to 1.6 and n2 equal to 1. So here you can see that the glass with n1 nearly equal to 1.6, our material is nothing but glass. So when I am talking about n1, I am considering material to be glass. Okay, and when my n2 is 1, then actually I am talking about material to be air. Okay, and then another interesting fact is, so this is nothing but contour of Rp. So this is contour of Rp as function of N2, refractive index N2, and angle of incident theta I. Okay, so typically you will be finding when value of theta I is less than 30 to 35 degrees Celsius. This is close to 30 to 35 degrees, sorry, not Celsius, degrees angle. So when incident angle is somewhere close to 30 to 35 degrees, then below that, you even if you keep on changing the value of refractive index, your Rp value is not actually changing. Okay, but if you go above this, then you will be finding that upon increasing the Rp up to some value of refractive index, you will be finding value of Rp to be 1, and after that value of Rp will be decreasing drastically to 0.2. Okay, so it means that if for an optical probe you can keep your angle of incidence greater than 35 degrees, okay, to the interface, then when the value of refractive index will be changing from one fluid to other fluid, there will be drastic change in ratio of amplitude of reflected wave divided by the amplitude of the incident wave. Okay, so it means that if you have to design an optical probe, you have to mainly operate in this particular design, like your angle of incidence of the ray should be greater than 30 to 35 degrees. Is this point clear? Now let's see the typical configuration at the system level. So at the system level, what we have, this is a pipeline, and in this pipeline these gray colors parcels nothing but represent, say, bubbles. These are the gas bubbles, and surrounding fluid is liquid. Okay, so in this system I have placed one sensing element over here, and this particular sensing element is actually called as probe. Okay, and as in this probe we have one light source over here, and this light source is then connected through one optical fiber. So this light source is connected through the optical fiber to this sensing element, and once it is getting reflected from the sensing element, then again that light is coming back through the same fiber, and then the other end of the fiber is connected to a detector, okay, which will be actually recording the reflected intensity of the light. Okay, now here we are having actually two types of possibilities. If I have gas, okay, so in case if probe is just adjacent to the gas, so if probe is adjacent to the gas, in that case we will be finding that probe is made up of glass, and first light is coming through glass having index of 1.6, and then it is facing some gas which is having refractive index close to 1. So here we will be actually finding the significant reflection of the wave. And in the second case, when you will be finding that your probe is in contact with the liquid, typically the refractive index of the liquid will be close to that of refractive index of the glass, and in this scenario you will be finding that there is no reflection. So in one case there is no reflection, in other case there is almost total reflection. Okay, so depending upon that, when your input signal is coming, in case of total reflection, that will give you significant output at the detector, and in second case, when there is no reflection there at detector, you will not be finding some signal. Okay, so it means that the location at which you have placed the probe, corresponding to that location, you will be getting your phase density function. Okay, phase density function means either you will be getting a output or you will not get any output. So if you are getting output, it means you have presence of the gas. So phase density function of gas is equal to 1 and phase density function of liquid is equal to 0. And if you are having the reverse situation, in case of reverse situation, what will be happening? Say if liquid is there, then at the output you will not be having any signal. So corresponding to that, your liquid phase distribution function will be 1 and gas phase distribution function will be equal to 0. Okay, so this is the typical structure, and then this probe, the shape of the probe is again an important parameter which will be actually many times controlling the way our measurement is actually being affected. So one of the shape which is typically, that is conical shape. So here if shape is conical, then this is the incident ray, and then it is reflecting like this and going back like this. And if your shape is cleaved probe with flat surface at 45 degrees, then you will be having incident ray coming something like this. It will be reflected from here. Then at this point we will be having actually nickel chromium coating which will act as a mirror, and this will again reflect the wave back to this, and almost it will follow same path. The reflected wave will also follow the same path. Okay, and third type of probe is U-shaped probe. So in case of U-shaped probe, it will be moving something like this. Okay, and all these probes are nothing but made up of glass material. So one important point we have to know that when we are using this optical probe method, so in case of X-rays, what was happening? We were not putting anything physically into the system. So if we were not putting anything physically into the system, it means that method was non-intrusive method of measurement. But in case of this optical probe, what we are doing, we are putting some glass tube, very thin glass tube, which is connected to optical fiber, and then a light source and a light detector. That particular glass tube actually we are inserting into the flow field. Okay, so this is nothing but a destructive method of measurement. So in this case, what will be happening, if the size of your probe is significant, then ultimately the presence of the probe will change locally the flow field, and it may actually associate, it may relate to changes in your flow patterns. Okay, so that's why the size of probe has to be selected so small that it does not make some significant changes on the flow field. Okay, so that is the reason typically if you will be finding, then it may be of the order of 10 micrometers or even of the order of 1 micrometer small. So very fine thin tube you will be finding, and typically the cost of the each optical probe may be up to some lakhs, say 10 lakh, 12 lakh of this small system only. Okay. So, because of this very small size, this conical shape find huge difficulty in providing the proper angles over here. So that's why from the manufacturing ease perspective, in the present scenarios, this type of probe is actually popularly used. Okay, and in the past, due to the manufacturing difficulty of cutting the sharp angles with symmetric orientation for very small size, this U type of probe was used. But once this flat faced probe has come, then actually the use of U probe has kind of become obsolete. Okay. So that is the evolution, but only one important point is what this optical probe is giving at a particular location where it is located. At that point actually it is giving me the value of phase distribution function. So it means that if you have to determine the void fraction, what you need to do, you need to locally move the location of the probe to different points along the cross section, and then you need to reconstruct the entire phase distribution function and then integrate in order to obtain the value of cross section average phase fraction. Okay, is this point clear? Now there comes one important aspect. So what output signal we will be seeing? So typically output at the output we just place photodiodes. So what photodiodes do? So depending upon the intensity of light signal, they generate some voltage. Okay. So in this output signal, you can see this output is plotted as function of time, and then corresponding probe location and bubble profiles are also actually shown over here. So this is the first orientation. In this case, you can see this is the bubble, and this bubble is actually approaching. Once it is approaching, corresponding to this probe is purely in the liquid medium. So as it is in the liquid medium, there will not be any reflection, because of which I am not having any voltage at the output or very less voltage at the output. Once my bubble has just reached very close to the probe, then slowly my signal will start increasing. And when the bubble is completely protruded into the probe, then I will be having actually some high signal, okay, till the time bubble is actually within the tube. And once bubble is about to leave the tube, corresponding to that, again I will be having actually decrease in signal when again I am having probe is actually particularly in the pure liquid. Okay. So typically what we can think of that simply I can take, say, some cutoff criteria S, above which I will be having bubble, and below which I will be having presence of liquid. Okay, but you can see this latency period over here. Okay, so why this latency period is actually coming into play? So the thing is, actually we consider that almost this is the point when bubble is just about to approach the probe. Okay, after this point there will be increase in signal, but whether bubble has actually reached the probe or not, that we are not knowing unless or until my signal is reaching to this point. Okay, so I'm having some latency period over here, and why this latency period comes into picture? Because I told you that the material of the probe is glass, and glass typically for majority of the liquids is having hydrophilic nature. Say if I talk about water, then it is having hydrophilic nature. Okay, so water drops typically stick to the glass surface. Okay, so because of this hydrophilic nature, if you zoom in into the probe, you will be finding that this is your probe and this is the interface. So this interface means below this interface you have gas and above this interface you have liquid. So because of this hydrophilic nature, you will be finding that in between the interface there will be presence of a thin liquid film. Okay, and this thin liquid film is majorly responsible for this latency period in this particular system. Okay, so because of this, what is typically done, rather than defining a common cutoff criteria below which we say that we have bubble and above which we say that below which we say that we have liquid in front of the probe and above which we say that we have gas in front of the probe, what can be done, a separate cutoffs S1 and S2 can be decided, and depending upon their separate cutoff values we can say that up to this point we have gas bubble, and then this is the latency period in which we will be having presence of a thin liquid film between the probe. And typically if you have to go for accurate measurement, your latency period should be as small as possible, because that is the period corresponding to which you will not be able to precisely tell that whether you have liquid or you have gas across the full profile of the bubble. Okay, similarly once gas is leaving the surface, then also you will be finding some latency period delta T2. Okay, so as I told you that this type of probe will be giving you nothing but the phase distribution function. So phase distribution function also you will be expecting something like this. So if you see phase distribution function Pk, particularly for gas, then this will be 0, okay, and then up to I am reaching the value of my output signal is reaching to S1. Up to that I will be getting the value of phase distribution function to be 0 only. And after this point I will be having unity value, and then again up to the value of S1 this will be unity, and then it will become 0. Okay. So ultimately what is happening, this is the point from where signal has become other than the pure liquid signal. Okay, so because of which this much portion of the length is something which will be giving me error in my measurement. Is this point clear? So this much portion, because I am considering that gas is only in this point and liquid is before this, so this is my error. So more is the latency period, more will be actually error in your measurement of void fraction. So that's why the orientation of the probe we have to select in such a way so that the latency period is actually minimum. हाइड्रोफिलिक इसलिए because this material is glass, so we need a see-through material, so that is glass, and its nature is that with majority of the liquids it's nothing but a hydrophilic. Okay. Okay, so all are clear with this method, optical probe. Then let's talk about next method, which is called as electrical impedance method. Okay, so electrical impedance method is again a very popular method for measurement of void fraction, and the benefit of this method is, and this particular method actually utilizes the power of difference in electrical conductivity of the two fluids as the fundamental principle of measurement. Okay, so here you can see this is one typical probe. So in this probe you can see you have one outer cylinder electrode, and then you have one inner electrode, and in between inner electrode and outer electrode you have some insulation, electrical insulation. Okay, so typically what will be happening when you have these two electrodes, okay, and in between these you have some insulation, once you will be making the contact of these electrodes with a electrically conductive fluid, these will be actually allowing the current to flow through it. And once you put in some fluid which is not electrically conductive, there you will not be having flow of current. Okay, so that is something which is the fundamental principle. This is typically called as electrical impedance method because originality of the fundamental approach comes from measurement of resistance, but measurement of conductance is actually more easy in comparison to resistance. So that's why sometimes it is also called as electrical conductance approach, and majority of the time it is used in a conducting way only. Okay, so here you can see that this first probe is a conical shaped, and in this first probe the location at which this probe is located, corresponding to this, it will be giving you the value of phase density function. Okay, so if you have current signal in the circuit, it means you have a conductive fluid. If you don't have current, then it means you are having the non-conducting fluid. So this you can employ only for the systems where you have actually difference of conductance. Okay, so if electrical conductivity of the two fluids is different, then only you can actually employ this system. Okay, and then this is the first type of probe. Then second type of a probe is in which we have actually two wires. So these are two thin wires. The diameter of these wires can be of the order of 1 micrometer or even smaller, because again these wires are actually coming into the flow field. Okay, so we don't want flow field to be changed or disturbed because of the presence of these wires. Okay, so whenever you will be placing these two wires into the pipe cross section, you will be finding that the length of these wires up to which you have presence of conducting fluid, corresponding to that it will be giving you the this so whatever output you will be getting, basically that output will be nothing but the function of the length up to which these two wires are actually filled with the conductive liquid. Okay, is this point clear? So typically resistance is nothing but function of length. So if your more length of the wire is these two electrode wires is actually filled with the conductive liquid, then you will be having more conductance. If it is filled with less conductive liquid to more portion, then you will be having less conductance. Okay, so depending upon this, whatever the output you will be getting, that output can be simply correlated with the length of the fluid which is present in this system. Okay, so that way you will be getting nothing but the value of linear void fraction. So that is the benefit of this second approach. So the first approach, where we were having two coaxial electrodes, this was applicable only for a particular location where probe is located. So this was giving you the value of local measurement of the phase density function or phase distribution function. Okay, but this second wired electrodes, what these are doing, these are actually changing the output signal in a linear relation to the length of the conductive fluid along the wire. So that's why in this case you will be knowing the exactly the precise length of the conductive fluid. So if you are able to predict the length, it means you are getting nothing but the value of one dimensional void fraction. Is this point clear? Because you can know, if say your total length of the wire is L, you can know that this is L liquid and this is L gas. Okay, so L gas by L, it will be giving you one dimensional void fraction. So benefit of this is you can measure actually one dimensional void fraction. Okay. Then one third modification is also done, and the basic idea of third modification was to design probe in such a way so that you are not getting any flow disturbance because of the presence of the probe. Okay, so that you can get actually non-intrusive measurement. So in case of non-intrusive measurement, actually two ring electrodes are placed at different lengths along the flow direction. Okay, so this is one ring electrode, this is other ring electrode, and this is my flow direction. Now in the flow direction, whenever the portion up to which along these ring electrodes you have conductive fluid, corresponding to that actually it will be giving you the output signal. Okay, so for here, in order to generate an output signal, the contact should be in this direction. So typically the spacing between these two metallic wires is actually very, very small. So it may be of the order of 1 mm or even small. Okay, so very small spacing. So that if a very small bubble is coming, that you can actually detect between the electrodes along the length. Okay. So benefit of this is, in this case, you will not be, yes, flow disturbance will not be there. Okay. Then again one more characteristics of fluids is there. So typically fluids may have different dielectric constants. So depending upon their different dielectric constants, they can give actually different values of capacitance. Okay. So typically for a two-phase mixture, the value of capacitance can be written in terms of some factor K times dielectric constant of gas multiplied with void fraction of the gas, then dielectric constant of liquid multiplied with void fraction of the liquid. So 1 minus epsilon, and this K is typically a factor which depend upon the geometry of the probe and the flow pattern. So what is the flow pattern and what is the geometry of the probe? So on these parameters this actually depends. Okay, so here you can see the first arrangement is flat plate electrodes arrangement. So in case of a flat plate electrodes arrangement, this is the cross section of a pipe. In this cross section of pipe you have this as one fluid and these are other fluids. So here this is one electrode, this is second electrode, and then you are measuring the values of capacitance across this. So once you measure the value of capacitance across these two electrodes, then what is the void fraction of the mixture that will be controlling the value of the capacitance. So that's why the benefit of this type of probe is it will be giving you two-dimensional void fraction. Is this point clear? So because in this case, depending upon the mixture of the two fluids, actually your value of capacitance is controlled. So if you, what you do, if you intentionally vary the void fraction, if you control the void fraction for a known situation, and then if you measure the corresponding value of capacitance, you will be getting some relationship, and with the help of that relationship then you can apply this for unknown situations to predict it. Okay, because this is so direct relation, but only this K is something, a parameter which is dependent upon geometry and the flow pattern. So that's why we need to perform calibration in order to determine the value of K. Is this point clear? But benefit of this is that we are directly getting the two-dimensional or area averaged void fraction. Okay. So in this configuration now we can have different arrangements to improve the accuracy and reliability of the system. So second approach is multi-electrode probe. So here you can see these are one set of electrodes which are connected to this terminal, and these are second set of electrodes which are connected to bottom terminal. Then third approach is this system you can also extend to calculate some localized volume averaged void fraction. Okay, so if you want to apply this system for volume averaged void fraction, then you need to actually extend these probes along the length. So once you extend these along the length, so we have this helical wound probe. So one set of electrodes are this and these are other set of electrodes. So these are wound helically along the length of the pipe. And then finally you have some concave plate probe. So here you have set of these plates which are actually wound along the length of the flow, and then these plates are actually connected to one another through terminals. Okay, so typically in these bottom two configurations, in first two configurations, if our electrode thickness is small, okay, electrode thickness is not too large, then we can measure area averaged volume fraction. But if we want to measure volume averaged void fraction, then typically we can go for these type of configurations where along the length we will be having actually significant length of the electrodes. Is this point clear? So typically in a capacitance, depending upon the dielectric strength, you get the output. Okay, and whatever your overall capacitance is, that is depending upon the void fraction. So this is the rule. So dielectric constant into corresponding void fraction. So depending upon this mixture rule, actually you will be getting the output. Whatever distribution you have, you are not concerned. Ultimately, it will be giving you the simple value of the void fraction. Okay. So you may have stratified flow, you may have bubbly flow, or you may have any other flow situation. So in this case, because you are getting the averaged quantity, so you are not at all concerned about the flow pattern. But the value of this parameter k is something which depends upon geometry and flow pattern. So that's why we need to do calibration. Okay. Okay, now comes next part, flow visualization. Okay. So till now what we have done, here actually our major interest was in knowing the value of void fraction. Once we have known the value of void fraction, then what we need to do, then our next interest comes to know the distribution of phases present in the system. Okay, because you may have two different situations where void fraction is same but distribution of phases is different. So if you have distribution of phases different, you will be having actually presence of different interfacial area. And if you have different interfacial area, that will be significantly controlling the rates of heat transfer, mass transfer and chemical reaction. So because if you have two fluids, then the transfer of property takes place across the interface, and to determine the transfer of properties, you need to know the interfacial area, actual value of the transfer of the property. Okay, so that's why, because for same values of void fractions, you can have the presence of multiple flow patterns. So that's why the knowledge of flow pattern or distribution of the phases is also very important if we need to actually, if we need to determine the values of interfacial mass transfer, heat transfer or any interfacial chemical reaction which is actually taking place. Okay, so that's why this is important. And the complex interfaces between two phases, if you have complex interface present between the two phases, then we know that we will be having actually multiple scattering of visible and near visible radiations, because more is the interface, then say at one point it will be first reflecting, scattering, so many things will be happening. And depending upon the nature of the interface, whether interface is chaotic or simple, you can have multiple of these scatterings. Okay, so typically what we need to do here also, we have to devise our instrument in such a way so that we can discriminate between some physical property. Okay, and typically the physical property for two phases is attenuation coefficient or electrical impedance, etc. So whatever the properties are there for void fraction, only similar type of properties we will be employing here, but the only difference will be that while we were doing the measurement of void fraction, then while we were doing measurement of local void fraction, then we were actually interested in only determining phase density function at a single location. And if we are doing the gross approaches, then we are able to determine complete void fraction across the entire cross section. Okay, so now what we need to do, whatever the previous methods we studied, we need to extend these methods only for measurement of local phase distribution function, such that the information of local phase distribution function is simultaneously known at majority of the points of the cross section. Is this point clear? So overall idea is we have to know the local phase distribution function only, because that is something which will be telling us whether at that particular location we have a liquid or we have gas. But when we were measuring the void fraction, then void fraction, considering it to be some time averaged or other quantity, we were actually just measuring this local phase distribution function at a particular location at a given time. Okay, now that local phase distribution function we will try to measure at majority of points of the cross section if we have to construct some phase distribution profile at a particular cross section. So simultaneously at a given time we should know the value of phase distribution function at multiple points of the pipe. So my meaning is, say if this is my pipe cross section, say this is some grid structure I have constructed. So at this point, this point, this point, all the points I should know simultaneously the values of phase distribution function. If I know the values of phase distribution function at the same time for all the points, then somehow I can employ some algorithms to reconstruct the profile. Okay, so that is the whole idea. So when you will be using the say opaque pipe materials, okay, so opaque pipe materials will not be having optical access. So in these scenarios what we need to do, we need to again use the radiations which can penetrate through the optical pipe material. So means we need to use either gamma rays or x-rays, etc. Okay, so typically when a beam penetrates a specimen, it is attenuated by the sample material, and if it is detected by a two-dimensional imaging device. So what I am saying, say I have given a beam, so its intensity will be decreasing, okay, and if say I give a beam something like this at certain angle, means instead of giving a single beam which is passing through this point, if I give my beam something like this, then what will be happening? My beam can cover most of the area of the pipe cross section. Now here, if I use some detector which is nothing but a two-dimensional detector, not a linear detector, if I use a two-dimensional detector, then what I can do? I can know the information about majority of these points. Okay, so majority of these points. So this type of information then I can later utilize to reconstruct the information, because this two-dimensional detector can give me more amount of data along all these individual directions. Okay. So typical systems are X-ray radiography. So typically the attenuation of X-rays depends upon the charge density of the electron. Why charge density of electron clouds? Because X-rays interacts with the, in the previous lecture I told you that if I have a nucleus, around the nucleus I will be having electron cloud. Okay, so X-rays interfere with the electron cloud. So once these are interfering with the electron cloud, their attenuation depends upon the charge density of the electron cloud, and as atomic number increases, X-ray attenuation increases, because typically the number of, yes. Then second method can be neutron radiography. So in place of sending the X-ray particles, if we send the neutron particles. So neutron particles basically interacts directly with the nucleus. So that's why their attenuation will be for some light materials such as hydrogen, boron and lithium will be high. However, these will be penetrating with the materials like heavy materials like lead, iron, chromium, etc. Okay. And typically the use of X-ray and neutron radiography is useful for thick walled pipes which contains fluids at high pressures and temperatures. So this is one approach which is called as radiography. Radiography, like you will be using either gamma rays or X-rays. Now how these will be used, that I will show you subsequently. Okay. Then second is tomography. So tomography is not any special technique, but tomography is a generic name. Okay, generic name means if I have number of experimental techniques, any number of experimental techniques, all which allows to visualize two-dimensional image of a given cross section of the measured object, that is something which is called as tomography. So it means if you are using the optical method for constructing the image, you will be calling it as optical tomography. If you are using X-ray method, you may call it as X-ray tomography. Okay, so tomography is a generic term for obtaining a two-dimensional construction of an object. Okay, and Of course, whenever we have to measure at a particular point, then our measurement should be simultaneously of a physical property in several positions on the measurement plane. The way I told you previously, that if this is my measurement plane, at all the points I should have the value of property known simultaneously. Okay, then only I will be able to construct the image at that particular time. Okay, and tomographic techniques provide a means of visualizing the internal behavior of two phases, and majority of the tomographic systems has been successfully employed for gas liquid three component flows, particularly in oil pipelines where you have gas, oil and water. So there also tomography has been applied, and even in case of gas solid flows in pneumatic conveying systems also, the applications of tomography people have already shown. Okay, and this is beneficial for online monitoring and control of industrial processes. So the benefit is, say if your system is so much efficient that at each and every time it can provide you photograph of a cross section and how phases are present in that cross section. Okay, so then you can keep a record of instantaneous phase distribution within the cross section, and at any point if you find some ambiguity is there, like whatever desired flow pattern was there, that is not coming, then what you can do, you can quickly actually control the system and then vary the process parameters. Okay, so that is the benefit, because whenever you see the operation of process industry, okay, so operation of process industry is not that simple that you can, if say some parameter is not coming correctly, you just switch off the system and then correct it and then switch it on. Okay, so typically if you think in terms of say a cement industry, so in a cement industry what you will be finding, at one location, say total area of industry may be 1 kilometers, this one cross section may be of 1000 square meters or 3000 square meters, and in that at some location there is one mill which is continuously grinding the material. At other location you have some furnace which is continuously heating the materials. All these things are nothing but interlinked to each other. Okay, so similarly in case of a say thermal power plant, okay, so in case of thermal power plant what is happening, at some point you have some pulverizer unit which is actually grinding the coal into fine powder, then that coal is entering into the furnace, then after that that furnace is supplying heat to water, then water is becoming steam, it is passing through superheater and then it is generating power. So it is not the case that okay, if one parameter of furnace is not working, just let me switch off the furnace and then I will control that parameter and switch it on. Okay, so if you see the process industry is like, you have to go for online monitoring. Okay, so typically whenever you see the once the boiler of a thermal power plant is stopped, it takes around 2 to 3 days to reach again the steady state condition. Okay, so it means the process is not that easy. So that's why typically you will be finding in process industry there are very planned shutdowns. So what they do, they have special schedule that okay, in 1 year for these 15 days or 20 days they will be going for the plant overhaul. So plant overhaul means they will be actually closing everything, and wherever they need repair and routine maintenance, that they will do and then again start the plant. Okay, so unless or until there is some very critical emergency accidental situation, they don't stop the plant. So if any routine maintenance has to be done, that happens in running plant only. Okay, so that's why my major point over here to say is that we have so many process industries, say chemical industry, these oil exploration sites, oil refineries. So everywhere processes are actually day and night happening continuously. Okay, so when the processes are happening day and night, you cannot always keep some human who is continuously looking into that parameter and then doing, because humans can make mistake and also that is not possible. So that's why you will be having requirement of such systems which can actually online control, online monitor, and then depending upon that monitor, if at any point you need to do the changes, then you can actually do that. Okay. And of course, as I told you that in majority of the process industries, you will be having actually presence of two-phase systems. So this is the principle of tomography. So here you can see that this is the cross section, this is some pipe, and in this pipe, this is my cross section. Okay. So I will be actually referring to targeting a particular cross section of the pipe. So if I simply see in this cross section, I will be having x coordinate, y coordinate, and say this is my distribution of phases present in the system. Okay. So what I need to do in this cross section, I need to insert some measurement system which will be actually measuring any property f which is a function of x and y. Is this point clear? So in this cross section, I need to put some sensors at each and every point of the cross section. To be precise, if I have to go for good amount of accuracy, but that is not possible. I cannot make continuous measurements. So of course, say I will be choosing some discrete points over here. And at all these discrete points, what I need to do, I need to actually measure the value of property f. And of course, the point which is in contact with the liquid, their value of f will be different, and the point which is in contact with the gas, their value of f will be different. So it means first thing I need to do is I need to measure f at the entire cross section, which will be function of x and y. Once I have measured, and of course this measurement is called as integral measurement. Why integral measurement? Because at all the points I have to simultaneously measure. Okay, there should not be time delay. If there is time delay, then it may happen that my reading of this point can be corresponding to some other flow distribution, and reading of this point can be corresponding to some new flow distribution. So if I am constructing the flow distribution at particular time instant, so or at all the points my measurement of the property should be corresponding to the same time instant. Okay. Then what we do, once we have done, so we call this as say phi n, and this phi n I have measured in say different directions zeta n, and then we will be using the reconstruction algorithm, and then we will be obtaining some new function f dash of x and y, and you can see that in the final reconstructed image I have shown that this was a circle, but here this is coming as a square. So that is depending upon the resolution of spatial resolution of the measurement. Okay, so that is depending upon the spatial resolution of measurement. Is this one clear? So it means this is a two-step method. In first step, we measure the property whose value we may think that will be different for liquid and different for gas. And in second step, we use that information of the data available at discrete points to construct in the form of phase distribution. Okay, so that is nothing but my reconstruction algorithm. Okay, so this is a two-step procedure. So whenever we are doing this type of measurements, we may have different types of interactions between sensor and flow. So first set of techniques, tomographic techniques, are called as transmission techniques. So in case of transmission techniques, what happens? The flow changes some physical property of the emitted field, such as polarization of electromagnetic waves or intensity of the electric and acoustic fields. Okay, so it means in case of transmission technique, if this is the cross section, wave is transmitted from one point to other point, and through this transmission, while it is taking this path, I will be having actually change in the signal. So in transmission technique means my source and detector are outside the cross section. Okay, is this point clear? Then I have second technique, that is emission techniques. In case of emission techniques, the sensor measures the radiations emitted by the material inside the measurement cross section, which can either be spontaneous or induced by sensor itself. So it means that outside this pipe you have some sensor. Now say sensor is like your camera. So in case of camera, what will be happening? Camera will itself send the light ray to the visualization window, and then that light ray will be reflected from the visualization window, and then you will be getting some signal, and camera constructs all these signals to give you one image. So it is something like that. So emission technique means the sensor itself is sending the signal, it is getting again reflected, and then you are getting corresponding value of the output. Okay, and third technique is called as deviation technique. So in case of deviation technique, flow changes the direction of radiation emitted, and depending upon the change in direction, then we will be finding that. So this technique is the one which I have actually given you idea yesterday. Let's say I have a source over here, then I have multiple sensors along the pipe. Okay, I have multiple sensors along. So once say this ray has come from the source like this, then at this point I have seen there is a bubble. Then because of this bubble, it has say reflected and gone to this sensor. So then I will be using this information, that if from this source to this sensor it is going, then at what location it could have faced the interface so that it has reflected in this way. Okay, so it means I have come to know about incident and reflected wave. So if I extend this incident and this like diametrical position of the source and diametrical position of the sensor, their intersection will tell me that at this location I have presence of interface. So this is for one measurement, but likewise I have to do the multiple measurements. Okay, and then club together their data to then reconstruct the profile. Okay, is this one clear? So whenever we do the reconstruction, of course in reconstruction in a single go we will not be getting precise output. Okay, so what we do, whatever my reconstruction algorithm has given the output, that output again through some mathematical descriptor we send back as a feedback signal to the system, and then based on that feedback it gives a controlled signal, and then again we keep on optimizing it unless or until my solution is converged. Solution is converged, it means the two simultaneous photographs in the two iterations, these are actually almost resembling. Okay, so of course for different techniques these mathematics will be different, so that is something which we are not doing. So I am just giving you the idea of general process. Okay, so okay, then we will discuss these 2-3 slides in the next class only.